delighted to have an expert in the area, Matt DeMott, who actually currently is the architect in GM's Manufacturing Data Analytics Advanced Development section, our team. And Matt, actually, I know Matt since he was a student, and he started at GM 7 years ago as the entry-level employee. And over the past 7 years, I think Matt applied his expertise in AI, data analytics, to truly participate in GM's transformation from a traditional manufacturing, fashion, to industry or manufacturing 4.0, capped by those keywords like smart manufacturing, like digital twins. And not only that, I think Matt has received several awards, including the recipient of the 4 Secrets. I think you can talk more about that maybe. And also, he actually is the finalist of GM's Next Generation Leadership. And the project that he led has won 2 times the recognition by the National Manufacturing Council in this country. And indeed, great job. Look forward to your talk. Yeah. Matt DeMott.
Thank you. Yeah, so good afternoon, everyone. I think Dr. Ming introduced me better than I could, so I appreciate that. But I'm excited to talk to you guys about what, I'll use the terms manufacturing 4.0 and industry 4.0 a little bit interchangeably, so they mean the same thing, and I'll dive into what that looks like. But this is a really important topic to me and to you as if you're a student, a researcher, or a future leader or professor. So I'm going to walk you through the roadmap of our, I'll call it a journey or an adventure today. So we're going to start off, I'm going to share a little bit about me, who I am, and why you should listen to me, if you so choose. The history of the Industrial Revolution. We'll also take a look at a case study of a real manufacturer and the challenges that a lot of manufacturers are facing. And then also, not just about the problems they're facing, but how we can have a data-driven future. And then if you're a student, what kind of workforce skills you might need to be successful in this area. Starting with me personally, my background, my faith in Jesus is the most important thing in my life, and so that drives me. Also, my family, that's my beautiful wife. We got married a couple years ago, and our dog Milo, he's crazy, but we love him. And then I'm actually 4th generation GM. My mom went to GMI Kettering, and then my dad also worked for GM, but my great-grandfather was in the Flint sit-down strike, and my dad actually graduated from UM-Flint. And I was born in Flint, so I've started off here and happy to be back. And so why should you listen to me? I have a lot of experience in this area. This is supposed to be a joke about being smart, but I'm really not that smart. I just have some experience. So I started at GM, like Dr. Ming said, 7 years ago. Before that, I got my bachelor's in computer science. I actually had Dr. Ming, like you said, as a professor. If you haven't taken one of his classes, would recommend, great professor. And then I finished my MBA just last year. And then I started my journey at GM in 2018. I was an intern before that. And I actually did a rotational program where I worked in the manufacturing plant where I ran the assembly line. I worked on the IT side deploying solutions. And now I've worked in the big data platform that we use to do smart manufacturing. And I would say if you're not convinced by some of those experiences, that's totally fine. But the application I lead is responsible for saving almost $400 million in profit opportunities, so preventing the line from going down before it does. And my project has received a lot of awards, internal and external, to GM. It's responsible for over 15 intellectual property awards, and we collect over 1.4 billion records of data per day, and we're expanding even further. And when we go to smart manufacturing forums, we actually learned that's one of the biggest in the automotive industry. So got a lot of good experience there. All right, so before we dive in to what manufacturing 4.0 or industry 4.0 is, I want to give a practical introduction on what some people think it is and what it actually is. And so, show of hands, we're going to try to be interactive here. How many of you use smart devices in your home? Internet of Things devices? We got one guy. Okay, I got a few more. Okay, so the thing with that is, how much do those cost on average? Like 20, 30 bucks? I know I bought a bunch of smart cameras and smart light bulbs. You swap out a light bulb for $10. Cool. All right. And then you can turn on your heat and your air conditioning from your phone. It's great. And then also, like, what people think of, they think of that and they think of this. How many of you watch Marvel movies? I know I have. You've got Tony Stark, and Hollywood likes to show us what the future looks like. And this is what a lot of people think manufacturing Industry 4.0 will do for you. But this is the manufacturing reality. I know when I started at GM, I crawl all over the place in these plants, and I get all dirty and everything. And so there's big pieces of equipment in very extreme environments. It's very dirty. It's not fancy. These machines weren't designed by Tony Stark. They're designed by people like me, I guess. And then on the right-hand side, this is a CNC, and that's a fancy device that cuts parts and stuff. And some of these things are upwards of $200,000 a piece. So when you go to swap out your light bulb, you pay $10. When you want to upgrade one of these to be smart, it's not that simple. All right, so now that we've looked at kind of what it looks like in the manufacturing reality, I'm going to dive into the history of how we got here, the different industrial revolutions we've gone through. And so I'm no expert on Industry 1.0 and 2.0. I've got a little bit in 3.0 and 4.0, but the Industry 1.0 started with in the late 1700s, the mechanical and steam-powered systems. And then in 2.0, you get your assembly lines. Obviously we know Henry Ford and all that, and that's in the late 1800s. And then what I'm going to dive into a little bit more today is 3.0, because that sets the foundation of where we're at, and then 4.0, where we're at, and then some people say might be even in 5.0, depending on who you talk to. But the 3.0 is where you get the computer on the plant floor through like a PLC. And then in 4.0, where we're really at today and emerging into 5.0, is your cyber physical systems. And we'll take a look at what that looks like here in a second. We're stuck. It looks like we had some issues with the sizing. Hopefully it works out okay here. All right, so starting off with the history of Industry 3.0, this is essentially where we started getting PLCs. So that was about 55 years ago is when Industry 3.0 was really emerging in the late 1960s and early 1970s. And you can kind of, if you're not familiar with what a PLC is, it's a programmable logic controller. And essentially what that is, it's a computer on the plant floor. And it opened up a lot of possibilities in the manufacturing space. And I have to give a shameless plug. I'm from General Motors. And so the first PLC was designed with and for General Motors. And it really revolutionized what that means to do automation. But before PLCs, what we had were machines that were controlled by hardwired circuits and relays and things like that. And so in order to really change something in that system, you had to rewire the whole system itself. And that was obviously not very scalable. So they created the PLC to fix that. And these are still very prevalent in pretty much every manufacturing sector that's out there. And for those who are computer science oriented, when I first got into PLCs, I saw, it's like, this is kind of crazy. It's pretty similar to assembly logic. That's what ladder logic was created to represent the physical relays and wiring so that electricians could easily learn it. Now, that worked really well, and it still works decently, but there's some challenges with that, and we'll go into those here in a second. And then also introducing robotics and IT systems is another thing that Industry 3.0 is really known for. And so I spent a lot of talking about the actual brains of the operations on the plant floor, but then you get into robotics, and once again, shameless plug for GM, the first industry robot was installed at GM, and it revolutionized the robotics industry, and also CNCs were big. And then we also want to welcome the SCADA system. If you've heard of that, it stands for Supervisory Control and Data Acquisition, and also computer networks. This was a big change to the game. Now, keep in mind, some of these systems were handling 1 to 10 kilobytes per second, so very small networks. I know if you're any gamers out there, that's hard to imagine. People are like, oh, I have a gig network. Well, these are 1 kilobit per second networks, and it causes some challenges for us today. We'll dive into that in a second as well. So moving into the next gen, which is Industry 4.0, just a little bit of history about that. This started, in the late 2000s, around 2011, I think was when it was formally introduced. It was introduced at the Hanover Trade Fair in Germany. And it really started to gain momentum across the world in 2014, and it became pretty mainstream in 2016. But what does it mean? The foundation of this industrial revolution was focused on connected devices, sensors, the industrial Internet of Things, IoT, IIoT, and that enabled the monitoring of controls and the processes. The next big item that really came onto the scene was smart machines that take data and they adjust dynamically based off of the conditions they're seeing out on the plant floor. And that's where they kind of talked about the cyber-physical, you'll hear that word, cyber-physical systems. And also the introduction of cloud computing, which is critical for this large amounts of data that we're now collecting. And Industry 4.0 is really about connecting everything, whether it's machines, sensors, people, into a kind of a unified network of pieces out on the plant floor. And this is definitely a huge change because Industry 3.0, there's a lot of siloed data, siloed systems that couldn't integrate very well, and you couldn't have data-driven decisions that we now are looking forward to. So I don't know if anybody likes memes, but this sounds great, but let's take a look at what people are actually experiencing in the manufacturing environment. We're going to take a look at a quick case study. I think he was doing something. Oh, thank you. So we're going to take a look at a quick case study, and once again, this is generalized to protect the identities of certain manufacturers, but it's not one specific manufacturer. I kind of aggregated some of the challenges, and then we'll see what that looks like here. All right. So for reference, like I said, this is not an actual manufacturing company, but it describes the reality that I've seen and many others have seen. And the reason I gave you such an in-depth background behind Industry 3.0 and 4.0 is for you to understand what a device landscape looks like. So using PLCs and robots and CNCs. In this example in our case study, they have a mixture of devices. They have devices that are older than me. They have devices operating alongside that are within the last couple of years. And so you get different generations that have different capabilities. In addition to that, the manufacturer here has worked with suppliers to design parts of their system. And that's what I have on the slide as a proprietary black box system. So sometimes they might hire somebody who's really good at designing that part of the system, and they give it back to them. But what they do is they make it a black box. And there's not a lot of insight you can get out of that. It's contained, and it might be proprietary. And sometimes they'll even charge you to get data out of that system. So we have to deal with old devices, new devices, and also black box devices out there. And to complicate things a little bit further, you have hundreds of types of devices, all in the same environment, all from different manufacturers, and all produce different types of data. And so if you look at the data generation part of my slide, you might get temperature readings, quality metrics, cycle times, and in a lot of cases, there's not a standard way or standard format in which to collect that data. So that's what a real manufacturer, like in our case study here, is dealing with. Might need some help. Oh, I think we're good. Okay. Okay, so now we've looked at the device landscape, the data, and you'll hear IT, OT if you're not familiar with that. I think most people know IT is information technology. OT is kind of the plant floor, devices and networks down there. And so some of these networks on the plant floor, like I said, a long time ago, they were designed for 1 to 10 kilobytes. We've upgraded to 10 to 100 megabits per second, which is good, but there's a lot of data coming off of these plant floor devices, and so you can only do so much at a time. You also have your IT SCADA systems. Some of them were built on old technology stacks. I've even seen cases where people don't even have the source code for that system. It's just running, and they hope they don't have to make any changes to it. And at the same time, you have isolated data sets because you might have sprung up a system, and then that one's separate from all the rest of them. So you have these silos that they're dealing with. And then workforce engineering tools. I could have labeled this section Excel because engineers love Excel, and you might have a lot of knowledge bases that are in random Excel files that they send back and forth, emails, and you don't have that digitized. Now, for this case study that we're looking at, they're dealing with all these things, but they also have these digital aspirations. They want real-time visibility. They've heard promises of using AI to run their plants. They want to have predictive maintenance to prevent downtime. They've bought into this vision of improved throughput and quality monitoring and productivity improvements. And they want to know, when am I going to get a return on my investment? How do I get there? So we're going to take a look at maybe what went wrong for this case study. And I think we're stuck again. Thank you. All right, so they had a little bit of trouble in paradise. So let's take a closer look at some of what those manufacturers are struggling with. I'm going to start off with legacy controls. Like I gave you the history about traditional PLCs. They're still very popular across the industry. And I mentioned that there's ladder logic is the primary language that's being used. And so I just ask you to try to imagine programming something even semi-complex in assembly language. It becomes very cumbersome. And so you might ask yourself, why not replace that device? And if I ask you to think back to your smart light bulb being $10, well, a lot of PLCs, they're tens of thousands of dollars. And so you don't just swap them out. Plus, if you do swap it out, you usually need the plant to not be running. So some of our plants at GM run 24 hours a day, 7 days a week, and you have to have a scheduled downtime. And when you make that change, it can be very complex. You're replacing literally the brain. You're doing open heart surgery or brain surgery on this system and replacing it. So if you don't do it right, you can cause additional downtime to the system. Excuse me. In addition to that, you have a mixture of generations of things out there. Like I mentioned, you have some that are 30 years old, some that are 5 years old. And everything's a little bit of a snowflake. So if you think of a snowflake, they're unique in nature. Every single one's unique. And we deal with that out on the plant floor as well, because you can't get the data out in the same way for every single one. You have to code something new for that specific type of device. And I will say that you might think of like a Tesla or an Amazon that's cutting edge. A lot of those facilities they have are brand new, and so they don't deal with as much of this mixture of generations, but I'm sure they're starting to come across that as they go back into some of their plants. All right, so challenge number 2 is to do with networks, and adding to the snowflake statement that I mentioned earlier. Many of these older generation systems have older network communication protocols, so it makes it somewhat impossible to communicate with those devices without some type of converter to communicate. I also mentioned black box systems, as you recalled earlier. So these vendors, they'll create a proprietary communication protocol. You can only use their protocol for that. And sometimes, like I said, you have to pay them money to get data out of there if it's not in your contract up front. I'd say probably one of the biggest ones is the limited bandwidth and throughput in the network. So the data, in some cases, might be ready to pull out of that system, but you can't reliably get it out of that system without causing some type of downtime, because you're trying to, what we often see is you're trying to get an image out of a camera on the plant floor. And when you're pulling that out, it soaks up all of the network bandwidth, and then all of a sudden you're dropping critical messages for safety, and it shuts down your system. And as a quick stat that I found when I was doing some research on this was that 48% of devices use legacy field bus networks. So you might ask what a field bus network is. A field bus is a non-Ethernet network, and it has far less bandwidth than Ethernet. And some top out at roughly 0.5 megabit per second. That's not a lot of bandwidth to get data out and still run production. All right, so now we're going to move on to challenge number 3. This is in the IT systems area. So I mentioned earlier that legacy controls equipment, it's good at what it does, but it wasn't designed for this time and day and age for Industry 4.0. And so the same thing can be said about our legacy IT systems. They were designed on a base set of assumptions. In today's quickly evolving environment, you can't afford to be stagnant. And these older IT systems are often pretty rigid and typically require a significant amount of rework to accommodate changes in business environments. For example, a legacy system might have a fixed number of equipment that can be added to it. It can't handle the bandwidth or something like that. And once it exceeds it, once the business strategy exceeds that bandwidth or number of equipment, it can't adjust to that. So that's our issue with flexibility. Now for integration, as we know, technology is rapidly evolving. Everybody sees ChatGPT or whatever is out there, and manufacturers want to bring those new types of equipment or technologies into their environment. Many manufacturers, they do want to use these, but they'll run into a roadblock with these IT systems that might have important data, and they try to plug things in. They don't integrate very well because they're old. And what this often leads to is, okay, I'll go and find a tool off the shelf, I'll buy it, and I'll plug it in. And now I have a mixture of like a Frankenstein environment where it's very not rigid, it's very rigid and it's not flexible. And so it's very costly to maintain, and it can cause a lot of issues as you're trying to scale these things. The next item is scalability. Like I said, these systems were designed a long time ago, and many cannot handle the rapidly expanding equipment footprint or amounts of data. And each legacy system has its own quirks. And with that, it can stifle a lot of growth in the manufacturing environment. And what happens is you have to have an IT team that monitors these all the time and look for any pitfalls. Okay, I'm going to bring in this new system or new thing. Well, what could that break? We have to ask that a lot, and people have to spend a lot of time analyzing those things. And what happens oftentimes is they'll say, we can't accommodate this new requirement that you have on the business side. And so engineers are very crafty, and they'll always find a way to do it, but it might cause issues down the road. They might shoehorn something in, and that's what we deal with the lack of scalability of these systems in the rapidly changing environment. And I also have to mention cybersecurity. So somebody might have a good heart and they want to add a new device to the network to get that data out of there. Well, a lot of these devices are very old, and they weren't designed with cybersecurity in mind. So you add something to the network, and all of a sudden that is a cybersecurity vulnerability, and now you have to have an army of people to go and patch all those old pieces of equipment or systems. So we definitely deal with that a lot today at GM and other places. I think I need some help. Thank you. Okay, cool. Challenge number 4 is disparate data. So what we're dealing with here is you can think of data silos. So this might be one of the bigger issues that I face. You might call them data silos or data islands. So the data is scattered amongst different systems, and these older systems they can't integrate, so they strand the data. And the reason this occurs is because several years ago, teams might have needed a quality system, so they spun that up, or they might have needed a torque system to monitor torque on bolts on a vehicle or something like that, and they spun that one up. And each system calls the same piece of equipment different names. You have different naming standards, and it makes it very hard to integrate in that way as well. And so you have valuable data that's stranded by itself, and you can't take a holistic view at view of your manufacturing facility. And also say data format is a huge one as well. There's a mixture of unstructured and structured data, whether it be in the IT systems or in the equipment, and not knowing how to process that data in a reliable way, you miss out on unlocking a lot of value. And this often causes delays in data processing, and I'm going to talk a little bit more about this on our next slide as well. So I called this slide a challenge a data explosion, and you can think of it in the 3 V's: volume, velocity, and variety. So with volume, like I said, there's thousands of manufacturing equipment in the plant. There's hundreds of data points per minute that are coming up from those. And you also have different types of manufacturers for those equipment. You also have a velocity of data that you want to achieve to meet business needs. You need real-time insights. And when you have a lot of data with a lot of different variety of formats, there's a lot of latency that can come in. And what engineers sometimes will do, they'll downsample their data. So instead of getting one every minute or one every second, they'll say, I'll get a summary of that once every 10 minutes. And you lose out on a lot of important information when you do that. Oh, didn't mean. Okay. And then the last part is the variety. Like I said, you have a lot of different types of data coming up. So you have sensors, you have sensor readings, logs, images, videos, motions, cycle times, and everything's a little bit of a snowflake. I keep bringing that up because it's a huge problem. And it can be hard to scale this type of solution to store the variety and have it in the format that can be utilized. And it can be a downfall of a system for sure. All right, so I didn't come here to tell you about all my problems. That is half of it, I guess. And I thank you for your patience getting through that. But you had to first understand the problems that people are facing out there so that we can look at how we can move into the solution. So we're going to dive into how computer science can help overcome some of these issues. I don't know if anybody likes SpongeBob, but we're going to go into the future here. I see some people smiling at least, but hopefully people aren't too young to know the SpongeBob reference. All right, so let's first start with why we're doing this. Why are we trying to solve these issues? And the promises that people have bought into is having real-time insights is the first one. Like, I can open my phone on my bed in the morning. I can turn on the heat if it's too cold. I can see what the temperature is in my house. My wife waters our plants from her phone. We can see different things in real time. And that's what manufacturers want to do as well with their machine statuses, the quality of their process, with making sure you don't have a leak in your gas line, making sure you're not losing thousands of dollars in that way. And in the same way, you want to have continuous improvement, and anything that you miss as a manufacturer hits your bottom line. So if you ship a bad product, it hits the end user and they're not happy about it. If you have downtime, you just made less vehicles and you can't make as much money. And so a lot of manufacturers are what I call, they're data rich but information poor. And so I have the stat here that 72% don't use their data effectively. So you have a lot of data, you're paying to store it, you're paying to manage it, but you're not getting the benefits. And so if you move on to the next part of it, impact on performance, they bought into that, hey, I see other manufacturers that are getting 30% improvement on their throughput or improvement in productivity, and they want those things too. And so with that, the last one is empowering decisions. We want to be data-driven. And I'll give one example that we do at GM is some manufacturers do routine maintenance. So I'll send somebody out every weekend to go and check one piece of equipment, and I'll do all of them throughout the year. And I'm hoping to catch an issue before it happens. But what happens if you missed that piece of equipment, or you're about to get to it in 2 weeks and you didn't? What we'd rather have is a sensor on that equipment. You'd have an algorithm to monitor that, and you'd send out somebody to check it only when it needs to be checked. And that's what people want to do so they can improve their productivity and also reduce downtime issues.
Sure. Okay.
Okay, so would this be a presentation in 2025 if I didn't mention AI or machine learning? I think I would be booed out of here if I didn't. So what I want to start with is that I'm not a person that says AI is the only way to do things. I think depending on the use case, you have to pick the right tool. You don't always need a sledgehammer. You don't always need a screwdriver. Sometimes you need a different tool depending on the situation. At the same time, raw data alone is not enough. Power BI reports are not enough, especially if you have to have somebody monitor that report all day, every day. What if they're not watching it? And also, rule-based algorithms are not enough in certain cases. So here at General Motors, we use machine learning, and I have to keep some of this stuff at a higher level because it is intellectual property. But we use machine learning for better predictive maintenance is one example. And it helps cross-reference lots of sets of data all at the same time and predicts when something's going to go down before it goes down. So sometimes rule-based algorithms can only look at one or two variables. This looks at larger sets of data and helps us with that. And also, any professors in the room? Okay, close your eyes for the students here. How many of you use GitHub Copilot for programming or Cursor or something like that? Okay, yeah, I guess you're safe, okay. But I know I have. I use it every day at work when I'm programming. But if you think about the manufacturing plant floor, there's configuration of devices and code that goes in those devices as well. And at GM, we're bringing generative AI to those platforms as well, so we can configure things faster, deploy things faster, get vehicles out faster. Now, one thing I would say, another trouble in paradise thing that people deal with is how to scale machine learning and AI. I think everybody knows it's a competitive advantage if you can pull it off. But companies will invest a lot of money and time and resources into proof of concepts. They get a good result and they say, cool, we solved the problem. But then when they try to scale that, they run into issues. And a lot of times they'll hit a wall, especially with non-standard data or different situations that are similar, but not exactly the same. Another thing they run into is culture. People will say, I've heard people say it at the plant, that's never going to work. And sometimes when you're developing something, you need inputs to make it, train it better, get less false positives. But things fail because of that as well. And this is a slide I stole from my boss, but it's called the Valley of Death. And the reason I'm bringing this up is a lot of universities and R&D, they'll focus on the MRL levels 1 through 4, and that's manufacturing readiness level. And like I said, they'll get their benefits out of it. They'll say, yay, we've achieved it. But there's a lot of work that goes into scaling those things into hundreds of plants at a manufacturing facility or a company. And so what I'm going to dive into now is how can we get past MRL level 4 and scale it up into all the way to the right where you can apply it to multiple plants. And it's more than just AI, ML we're going to talk about. All right, so the first thing we do need to do, I said, and I'm not lying that we can't upgrade everything, but sometimes you do need to upgrade certain things. So I'm going to start with hardware. Sometimes you need to do machine learning AI on the edge, and sometimes you need to do it in the cloud. And so I think this is where we're going to run into the end of the traditional PLC. So like I said, PLCs use ladder logic. They only have so much processing power, and it's hard to do complex analysis of data on a traditional PLC. And so this is where we go into a hybrid approach where you can have both a traditional PLC and a soft PLC, which is more PC-based. So the benefits of a soft PLC is it's PC-based, so you have higher level languages, you have more processing power, it's easier to integrate with upper level systems, and it's cheaper to upgrade. So with cybersecurity, we have a lot of devices that were designed to last 20 or 30 years, but with cyber threats coming in, sometimes you have to replace things, and PC-based is a little bit better. But if you pair that with a traditional PLC, and those traditional PLCs are lightweight, they have very quick scan time, and they can do safety transactions a lot faster. And so if you can mix those two things together, what you have is you have the benefits of the traditional, you can run edge computing, and you can also get your data up to the cloud for training of models and other more intensive analysis. So I do think there is some room for upgrades, and I think there is a shift in this capacity to enable edge computing and integration. All right. So this topic here, data context, is a bit near and dear to my heart. I know I don't think a lot of people are discussing this as much in the industry as they should be, but contextualization of data is really important. If you don't have the proper context to your data, you can't really do much with it. And due to the many issues I've discussed earlier, a lot of people will push the context or how to format the data in the end device. And now that's really important, but it doesn't capture. You can't end the journey there. So if you take a look at the right-hand side of the slide here, I'm going to walk you through some complex relationships that are out in the manufacturing plant floor. So you might have a PLC, it controls a robot. That robot will either pick up a part or weld something, or put dispense out, do any number of operations. It might have a weld gun mounted on it, and it should take about 18 seconds to do that operation. So this is how the system is designed. And if you don't have that context, you can't unlock as much value. And so this unlocks a lot of possibilities. You kind of represent the plant floor as like a graph-like relationship. And this allows for workforce efficiency gains and the use of generative AI to configure things and have more insights into your data. So what do a lot of industry partners do? They use commonly used standards like US Car 53. Once again, shameless plug for GM. We're part of a forum with Ford and Stellantis, where we're pushing down to the suppliers in their end devices. You should produce your data in a JSON format. It's a lot easier for an upper level system to contain or consume, and also using like an open protocol like MQTT to convey that. So that way I don't have to have a snowflake model for every single one. And also a lot of industry folks will focus on ISA 95, which is more focused on how you integrate upper level systems, how you represent things in terms of a hierarchy. Now, I don't think that goes far enough, but I think it is a good start. All right, so now on to the big data portion. So we talked a lot about the importance of getting data out of the system or out of the equipment, contextualizing it. But how do we store it? How do we use it? At GM, our manufacturing data analytics platform, like I mentioned earlier, is getting well over 1.4 billion data points from equipment every day, and it's growing more rapidly. And this is where kind of cloud computing is coming onto the scene. It's nothing new, but it's being embraced a lot more. And so there's a bit of a hybrid approach, like I mentioned earlier. Sometimes you have to do your edge computing for real time, and we're embracing that as well. But then you have to get your data up into the cloud. And these are the tech stacks that are often used. I'm not saying that it's one size fits all. There's a lot of different flavors out there that are similar, but a lot of people use Kafka for data streaming. They'll use Databricks and Snowflake or AWS, you pick your flavor, to storage and analysis, and then Spark for large scale batch processing or even streaming. And I can't forget about the digital twin portion of this space. What I struggle with is you go into a room with 10 people and you ask them what their definition of a digital twin is, and you come out with 11 answers. And that's the struggle with digital twins right now. I think a lot of people conflate 3D emulation or simulation with a digital twin. I tend to agree with, I went to a consortium at U of M Ann Arbor, and they mentioned that, and I agree with them, that you have to have real-time data feeding your digital twin. A lot of people will just have the 3D simulation, and it's like, well, that's just simulation with a view on top of it. I don't agree with that. And I will mention one thing as well in terms of analytics that a lot of people will dive into. Not every manufacturer has the in-house skills to do things like this. And so sometimes they'll outsource them. Another thing that people will focus on, I know at General Motors we do a similar concept, is we outsource if a supplier has a really good domain knowledge of, like, say, vibration is very complex. We do partner with people for those types of analysis. All right, so I mentioned several times probably in this presentation, maybe I have, I hope I did, garbage in is garbage out. If you don't have good data, you're not gonna get good insights. And so people will blame the technology, or they'll blame the algorithm or whatever it is, and they'll say that thing's not working, but really it was the foundational data. So one step is to make sure you're getting good data. So let's assume we've got that. The next step that I think is very important is the data modeling. How do I help find the nuggets of gold in that mining operation? And that's where data modeling comes in. So what we often do, and we're really leaning into, is you start by asking yourself, what kind of insights am I looking to get out of this system? And you kind of model those types of processes or equipment in the plant floor in your upper level system to give a real world view of the data. And what a lot of industry partners are doing is they're leaning into the medallion methodology. I'm sure you guys have heard of that, but if you haven't, it focuses on the bronze, silver, and gold layers. So you put the raw data in the bronze layer, you do your partial processing into silver, and then you have customized, very specific tables in your gold layer to give those insights for reporting and analysis. And that's where data engineering is really critical to do machine learning and AI at scale. So I know some examples in real life are, I've watched teams that they have very good skill sets in AI and machine learning, but they'll spend 80% of their time doing data engineering. And I think if you get a good data platform, then you can hit the ground running for when you're trying to make a new model. Okay, so for the students in the room, or I guess professors as well, if you want to know more skills, what workforce skills are needed and where do you fit into this? So I'm going to start off with, based off some research that I've done and things that I've seen in the plant floor, what are kind of some shifts in the manufacturing work? What's going away and what's coming in? A lot of what you'll see on the left-hand side is very manual things. It's not to say that people are going away. What it's saying is people are going to have to use more technology, more collaborative robots, more algorithms in their daily work. And so a lot of the people who are just purely not wanting to do anything with technology, that's not a realistic thing anymore. And also what's springing up is you need more people who can configure the smart devices, who can create the digital twins, who can be technicians or data scientists to use that data and get insights out. So that's what we're definitely seeing. And I would say that data scientist role is definitely changing with the advent of AI, but I don't think it's going away. And then what specific skills do people need? I will say that one thing that I've learned in my journey is there's a lot of skills you can learn, but if you don't work hard and you aren't a good person with good character, you're not going to go very far. So there's a lot of people who are smarter than me, but I might work harder than them, and that makes a big difference. But specifically, cross-disciplinary knowledge, that's where like people like me come in. I have a computer science background, but I work with a lot of business people. So you bridge the gap between the disciplines. So some people might only know the manufacturing space, and some people might know the IT space, and they can't program what needs to be programmed. And so that's where people like me come in, and I have both skills, and I can bridge the gap. That's not to say that people with domain knowledge are not important, because you need domain knowledge to have that deep manufacturing process knowledge. And if you can partner with a data scientist and help them program something new, that's where I've seen a lot of people be very successful with that approach as well. And then in terms of leadership and strategy, things are changing very fast right now. And you don't have to be a manager of a lot of people to make a big impact. You can be a leader even if you're not over somebody. And so if you can inspire people with a vision or see things before they're coming, that's very helpful. But the next thing is you have to be able to communicate that vision with people. And I think that's where there are some challenges. But if you can inspire people and you can share that and you can get people on your bandwagon, that goes a long way. And then continuous learning is always huge. It doesn't have to be just in the classroom, but always being willing to learn from other people, always being ahead of the technology curve as much as you can, learning, reading articles and staying ahead of the trends is really big. As far as technical skills, I mean, there's a lot, but I just picked a handful. Cybersecurity, like I said, if you put a device on the network and it's a cybersecurity vulnerability, can't have that. So we have a lot of people in cybersecurity is a big one. As far as big data, like I mentioned, data management and cloud computing skills are critical in this day and age. So that's definitely growing. I have to say AI, obviously. I was just reading an article this morning, and the number of job postings from just a few years ago that mentioned the use of AI, not even knowing how to do that, have that skill set, but just knowing how to use it. I think AI is going to be like the Excel of 2000. So if you don't know how to use it, you're not going to go very far. Data analytics, I would just say data literacy. Like I said, the data scientist role is changing, but it's not going away. In that article I was reading this morning, actually, they were saying that entry-level roles are going a little bit down, but the senior roles are growing. And so I still think it's needed. It's changing. And then I wish I would have taken more statistics classes when I was in college, to be honest. That would have been helpful. I did take some. I probably should have paid more attention. But I use statistics every day in my job. And so I would recommend those who want to get into data analytics to use those things. And then Spark data processing, like I mentioned, is huge. Finally, IoT and automation skills, being able to troubleshoot equipment. And so, like I said, PLCs are still out there, and they're going to be out there for decades, really. So being able to understand that and understand higher level languages and configuring devices and bridging that gap technically, not just from a leadership perspective, but technically is definitely crucial. So I think that's all I have. So thanks for listening to me drone on. I'm passionate about this, so hopefully that came across, but take any questions.